Hello, and thank you for your interest in using sPEGG. In these videos, I will provide you with a basic overview of how to set up your simulation using the sPEGG framework. We'll begin with the very basics, and I will walk you through how you can customize the sPEGG codebase to implement your eco-evolutionary model. As a very simple first step, we'll take a look at the hill climbing problem described in our accompanying manuscript. The videos are broken down into segments based on the functionality they implement. That way, you can watch them independently at your own convenience. A lot of this material covers the same ground as the tutorial on sPEGG's GitHub page. And of course, if you have any questions, please feel free to post a question to our user group list on Google, speg-users@googlegroups.com. Also, I want to mention at the outset that the approach I will describe in these series of videos is only one of several possible workflows. You might find another approach to better work for you. Let me give you a high-level overview of how our sPEGG simulation can be structured, and a map of how these video tutorials relate to that structure. First, we will have a simulation class that is responsible for running the simulation. This simulation class will be discussed in the present video, as well as when we bring everything together in video number 10. The species object will be responsible for actually implementing the key components of our eco-evolutionary model. In video 2, we will discuss how we set up and define our species object. Videos 3 through 5 discuss how we can specify the genotype-phenotype map, and introduce you to tricks we can use in other parts of our simulations. Video 6 will introduce you to how you can use sPEGG to simulate reproduction, which involves operations like choosing the parents. Similarly, Video 7 will describe how sPEGG transmits genetic information from parents to offspring. In Video 8, we described how we can update individual states in the simulation using concepts we learned in earlier videos. Finally, the input files will be discussed in video number 9. We will bring everything together in video 10, where we will also go over how data can be logged. A few preliminaries. First, this video assumes you are working in a Linux environment. You will need to have NVIDIA CUDA installed, as well as a library called libconfig. There are several resources out there about using these tools, so I won't repeat them here. So let's dive in. Let's begin by opening a terminal and clone a copy of the sPEGG repository. As you can see, I've downloaded the directory containing the sPEGG codebase. The first thing we'll do is navigate to our main directory. Inside, you will see several files in 2 directories. The header directory stores all your class definitions and .h files. The src directory, for source, stores the .cu and .cpp files where the functionality of your model is implemented. Inside the sPEGG directory, let's create a directory for the simulation we will develop over the course of these videos, called demo species. Let's begin customizing sPEGG inside this directory. We'll start by defining a simulation class that actually manages the simulations we're about to conduct. We'll create a new header directory to store the header files for our species. Now we'll want to populate this directory. The first thing we'll do is create a header file for our simulation manager. We'll call this demo species simulator.h. The first thing we do is define our header file and of course, don't forget the end if. Our parent class is going to be the simulation class defined in the main sPEGG codebase's header files. So, we'll need to specify that header file. We'll also need to include a header file for the species we simulate, which will be represented by a class called the demo species class, which we will note here. This means we should include a header file for this species as well. Finally, we'll include the statistics class so that we can keep tabs on what's going on in our simulation. We'll create a very minimal constructor and destructor, as well as a function telling our code to actually run the simulation. Notice these are all public members of the simulation manager. This means that these members of the demo species simulator class are accessible from other parts of our program. But we'd like to include a few members that are never accessible. So we'll mark these as private, and these are, first, an array of pointers to in-stochastic objects that will store our demo species. Second, we'll create a pointer to our statistics classes. Third, we'll have a variable that keeps track of the number of species we are simulating. And finally, we'll create a function that will be in charge of initializing everything inside the simulator. Now that we've defined our simulator class, let's sketch its implementation. We'll construct a skeleton of the corresponding .cpp file that implements the functionalities we've defined for our demo species simulator. Let's create and navigate to an src directory, and then create a .cpp file there called demospeciessimulator.cpp. At this point, we aren't invoking CUDA per se, so we can keep everything as pure C++. This enables us to later reuse this code if we want to create a CPU version of our model. Now let's include our simulation header file in the definition, and define our constructor. We'll just inherit straight from the constructor of the simulation class, which is the function simulation. Now to populate the constructor, let's specify the initial population sizes as being 10 individuals per patch. We'll also define the maximum number of individuals as being 1,000 individuals per patch. For simplicity, we'll only simulate one species, and let's call the private initialize classes function. Next, we'll specify how we want to do the initialization of our classes. So we'll specify our initialize classes function, which is a member of the demo species simulator class. Our first task is to define our array, which consists of pointers to each of our end species ins stochastic objects. Now, since we only have one species in this demo, we'll manually set the species ID to 0 here. Next, we'll note that the first and only element of our array is an object of type demo species, to which we'll pass the arguments. In video 2, I will show you how to create this constructor. Our next step is to instantiate a statistics object that will keep track of our summary statistics over n patches. And we are now good to go. If you'd like, you could also add a command to export the initial conditions for your species as a CSV file here as follows. Now at this point, we'll wait to implement the run function, but we'll revisit that once we've defined and initialized our demo species class. And finally, let's prepare our destructor, which will destroy each pointer in our array and finally delete our array, as well as the statistics object. So that's a skeleton of our simulation class. This provides an outline for the work that you will have sPEGG do. In the next video, we'll talk about the customized demo species object. Thank you again for watching, and if you have any questions, shoot me an email via our mailing list, speg-users@googlegroups.com.